Dr. Schreifels again, going to discuss an exciting topic on gases. Now, we discussed gases in my previous introductory video on gases, and I pointed out to you that there are mathematical relationships that exist between the variables that are used in describing ideal gas or gas behavior. These are the gas laws, which, remember, we reduced to the ideal gas law. Applications are of the density, using density to figure out molecular weight. Dalton's law says that the gases may behave independently of each other. Kinetic theory of gases, which allows us to figure out the speed of the gas. Graham's law, which allows us to figure out the molecular weight of a gas from the rate of effusion or diffusion. And finally, we have the van der Waals equation, which we would use for gases that don't behave in an ideal manner. I put those into a toolbox that I'm going to put in here. So this is our list of mathematical relationships that we would use to solve individual types of problems. So let's try it with a manometer problem. So we have that. Let's move this back up. So we have that, and we kind of do an inventory of what the problem is telling us. You have a keyword open-ended manometer, so that tells us that we need the first relationship. The liquid level is higher on the side exposed to atmosphere. That tells us that the pressure inside where the gas is greater than the pressure on the outside, which is the atmospheric pressure. So let's do an inventory of what is given. So here is our list of given terms. So we know that the height of the oil is 105.7 centimeters. We have to then convert that to millimeters, so there we've done that. And then the density of the oil is much less than the density of the mercury. So we want to figure out the height of what the height of mercury would be at that pressure. So we're going to go to our top relationship that deals with manometers and put that down here. And notice we have to maybe rearrange that a little bit, because we know the first three terms, density, height of the oil and density of the mercury. What we want to know is H2. So let's copy that, and we'll rearrange a little bit. To this. And then we need to take this and solve for H2. So we can do that by, let's just copy this again. And we're going to get rid of the D2 on this side and bring it over to the other side. So there we go there, and there's our final relationship that we're going to use. Now we can just insert the numbers. So we've already assigned the variables and are given. So now we put in the numbers into their respective places. Oops, wrong one. There's our numbers. I didn't put in the units just to simplify the actual math, the way it's written out. So we get a number for this. It turns out to be 58.64 millimeters of mercury would be what that height would be if we were using mercury instead. Now, this has to be added to the other height of atmospheric pressure height. So that was 754.87 plus the 58.64. That gives us 813.5 millimeters of mercury, if I'm doing the math correctly, which we can then convert to atmospheres by recognizing that 1 atmosphere, you have 1 atmosphere per 760 millimeters of mercury. Fix this. So do the math for that and you'll end up with 1.07 atmospheres. Whoops. And that's it. So make this, don't overthink this problem. I don't think it's as hard as it may have initially looked. Hope that helps. Thank you. Have a good day.